Hey Calculus class! Today we're going to learn topic 56, Calculus with Vector Functions. So we're going to start with vectors and parametric functions. There's a close connection between continuous vector functions and parametric curves. So suppose that f and g are continuous real-valued functions on an interval I. Then the set C of all points x, y, where x is equal to f of t and y is equal to g of t, and t varies throughout the interval I, is a parametric curve, we can think of C as being traced out by a moving particle whose position at time t is given by f of t, g of t. So here's a graph of C. So here is the moving particle being traced by this parametric curve. Then the vector function r of t, which is given by f of t, g of t, is the position vector of the point P of f of t, g of t on C. In other words, we are picking the origin as the tail of the vector, and the tip of r of t is tracing out the curve C. So this vector is starting here at the origin and is basically moving along the curve as well. So a vector-valued function, or a vector function, is a function whose domain is a set of real numbers and whose range is a set of vectors. So for example, in a parametric curve, we have that vector r is given by f of t, g of t, which would equal f of t times the ith vector plus g of t times the jth vector. F and g are called the component functions of r. The domain of r consists of all values of t for which the expression for r of t is defined. So for example, if we have a vector defined by the parametric curves 3t and the square root of t plus 2, that means we can rewrite the unit vector as 3t times the ith vector plus the square root of t plus 2 times the j vector. The domain would be represented by -2 to infinity. And I get this domain because I look at each component of vector r, and for the horizontal component, or the x component, basically t exists everywhere here, since it's 3 times t. And for the vertical component, the t will only exist from -2 to positive infinity. So since the domain consists of all values of t for which the expression of the vector is defined, so that means for whatever the restrictions are for t for either component, that is your domain of your vector r. Alright, so let's look at limits of vector functions. So the limit of a vector function r is defined if you have vector r equal to f of t, g of t, then we can say that the limit as t approaches a of the vector r is equal to the limit of the horizontal component, the limit of the vertical component, provided that the limits of the component functions of r exist. Now, a vector function r is continuous at a if the limit of the vector as t approaches a is equal to the vector of r at a. And this is our basic definition of continuity, that the limit exists, that the value of the function, or in this case the vector, exists at that t value, and of course the limit and the value have to equal each other. Alright, let's look at an example. So we want to find the limit as t approaches 0 of this vector. Notice each component is a parametric curve. So I'm going to take the limit of the horizontal component. So if I want to take the limit as e to the t minus 1 all over t, when I do this, if I was to plug 0 in, I'm going to get e to the 0, which is 1, 1 minus 1 is 0 over 0. I have an indeterminate form, so that means I'm going to L'Hopital. So I'm going to take the derivative of the top and the derivative of the bottom. And when I do that, I just get e to the t. And now when I plug in 0 for t, I get 1. Now I'm going to take the limit of the vertical component. If I was to plug in 0 here, I would also get 0 over 0. So I need to L'Hopital. And after I L'Hopital and simplify, I get 1 over 2 times the square root of 1 plus t. Now when I plug in 0, I get 1/2. So that means that the limit of this vector is given by the vector 1, 1/2. All right, let's look at derivatives of vector functions. So the derivative of a vector function is defined by the derivative of the vector r of t, dt, is given by r prime of t, which is equal to the limit as h approaches 0 of r of t plus h minus r of t over h. So this is just our limit definition of any derivative. And if we wanted to look at this graphically, right? So here we have r of t, the vector r of t, and then we have the vector r of t plus h. And the derivative vector is, of course, going to be the tangent vector at point P. And what that means, what we would have to take the limit of the slopes of the secant vectors until we get to our tangent vector. So the vector r prime of t is called our tangent vector. And the vector capital T of t is equal to the derivative of r of t over the magnitude of the derivative is called the unit tangent vector. And the unit tangent vector is the direction of motion of a particle with length of 1 unit. So this leads us to a theorem. If f and g are differentiable functions and r of t is equal to f of t comma g of t, which is equal to f of t times the I vector plus g of t times the j vector, then basically to take the derivative, you're just going to take the derivative of each component, the vertical component and the horizontal component and then the vertical component. All right, so let's look at an example. So we want to write the equation of the tangent where t equals -1, and we are given this r vector with this horizontal component and vertical component. So I'm going to take the derivative of each component. So this, of course, also gives me my velocity. So since this is my position vector, when I take the derivative of the position vector, I'm going to get my velocity vector. So I just take the derivative of the horizontal component and the derivative of the vertical component. And since I'm looking at t equals -1, I'm going to plug -1 into my r vector to get my basically my position at t equals -1. And then I'm going to also plug in -1 to my velocity vector to get that slope of the tangent vector. So this gives me the position, which is at -5, 11. This gives me the slope, which will be -9 over 12. And I got the -9 over 12 is because slope is defined as your change of y over change of x, which is basically your vertical component over your horizontal component. And that's exactly what I did. Vertical component over horizontal component. And then, of course, simplify to -3/4. So now I can go ahead and write my tangent to give me y minus 11 equals -3/4 times x plus 5. And then, of course, we have position, velocity, and acceleration vectors. So just like with any other function, the velocity and acceleration is found by taking the first and second derivatives respectively. So if we say that vector s given by x of t comma y of t is the position vector at any time t, then the velocity vector v is of course the derivative of the s vector. And then that means that the acceleration vector is the second derivative of the position vector. And we also have our direction, which will be given by the velocity vector over the speed, which is the velocity vector over the magnitude of the speed. The magnitude of the velocity vector. And this is what we call our unit vector. All right, so let's look at some examples. And all of these examples are examples of what you may see on the AP test. So if a particle moves in the xy plane so that at any time t being greater than 0, its position vector is given by natural log of t squared plus 5t, comma 3t squared. We want to find its velocity vector at t equals 2. All right, so since I want to find its velocity vector at t equals 2, I need to find my velocity vector at any given time. So what that means, since I'm given my position vector, to find my velocity vector, I'm going to take the derivative of the position vector. So in order to take the derivative, I'm going to take the derivative of the horizontal component and then the derivative of the vertical component to get the velocity vector to be 2t plus 5 over t squared plus 5t, comma 6t. And I'd use the chain rule for the horizontal component. Now, since I want it specifically at time 2, I'm going to plug 2 in for t to get 9 over 14, comma 12. All right, our second example. If a particle moves in the xy plane so that at any time t, its coordinates are given by x equals t to the 5th minus 1 and y equals 3t to the 4th minus 2t cubed, find its acceleration vector at time t equals 1. So basically it's the exact same thing. I'm given my position vector right here, defined in terms of parametric curves. To find my acceleration vector, I'm going to need to take the second derivative of each component and then plug in t equals 1 to get the actual value of the acceleration at time equals 1. So first derivative of the x component gives me 5t to the 4th. Second derivative gives me 20t cubed. First derivative of the y component gives me 12t cubed minus 6t squared. And the second derivative gives me 36t squared minus 12t. Now I'm going to go ahead and plug in 1 for t into each second derivative, and I get that the acceleration vector at time equals 1 is 20, 24. All right, now of course we also have integrals of vector functions. The definite integral of a continuous vector function, r of t, is defined by the integral from a to b of your vector function dt. Basically, you would take the integral of the horizontal component and then the integral of the vertical component. This is also known as the displacement of a particle from t equals a to t equals b. Now, if you were to take the square root of the derivative square of the x component, the derivative of the x component squared, plus the derivative of the y component squared, this is the speed of a particle, or the magnitude, aka length, of the velocity vector. Now, if you were to take the integral of the speed, this represents the length of the arc, or the arc length of the curve from t equals a to t equals b. Or you can consider it the distance traveled by the particle from t equals a to t equals b. All right, so now let's look at some more typical AP style examples. So this would be a no calculator example. A particle moves in the xy plane in such a way that its velocity vector is given by 1 plus t, comma t cubed. If the position vector at t equals 0 is 5, 0, find the position of the particle at t equals 2. All right, so where are we going to start with this one? Well, we know that we have our velocity vector. It says that we want to find its position at t equals 2. and we have its starting position at t equals 0. So basically, we're going to work with just the x component, or the horizontal component, then we're going to work with just the y component, aka the vertical component. So just like in any other type of problem that gives you the velocity and asks you to find its position after so much time, you have to, of course, start with its initial position. So in this case, for the horizontal, it started at 5, and then you have to add how much distance it traveled over that time interval. So for the x component, we know that we're going to want to take its initial start, which in this case is 5, plus the distance that the x component has traveled. So that's taking the integral of the velocity. Now I'm going to have to do the exact same thing with the y component, but this time I'm going to use the 0 for my start and the t cubed for the integral. So when I set them up, I have, for the x component, 5 plus the integral from 0 to 2 of 1 plus t dt. I'm going to integrate by hand because I do not have a calculator. So I get 5 plus t squared over 2, and I have to evaluate that piece from 0 to 2. When I do that, I get 9. Now for the vertical component, I'm going to have an initial start, which is 0, plus the distance it traveled in the vertical direction from 0 to 2 of t cubed dt. Integrate by hand, evaluate, and I get 4. So that means that the position of the particle at t equals 2 is at 9, 4. All right, let's go ahead and look at a typical open-ended question with vectors and parametric curves. So an object moving along a curve in the xy plane has position x of t, y of t at time t with dx dt equal to sine t cubed and dy dt equal to cosine t squared. At time t equals 2, the object is at the position 1, 4. So part A says to find the acceleration vector for the particle at t equals 2. And this would be an okay calculator question because I did not say no calculator. So since I'm already given my derivatives of the position, so aka I already have my velocity functions, to find the acceleration vector at t equals 2, I just need to find the derivatives of the vector of the velocity vector and then plug in t equals 2. So when I take the derivative of the derivative of x, I get 3t squared times cosine t cubed. I'd of course use the chain rule. For the derivative of y, I get negative 2t sine t squared, another use of the chain rule. Plug in 2 for each, and I get that the acceleration vector at t equals 2 is given by negative 1.746, comma 3.027. And yes, for the AP test, you do need to write, if it says find the acceleration vector, you do need to write your components in vector form. So for part B, write the equation of the tangent line to the curve at the point where t equals 2. So this is using the derivative of parametric curves, since we have the derivatives of each component. So in order to get the slope of our equation of the tangent line, we want to use the fact that we want dy dx. So we want the derivative of y in terms of t over the derivative of x in terms of t. So that means we have cosine t squared over sine t cubed. Now since I'm looking specifically at t equals 2, I can go ahead and plug in 2 for t to get cosine 4 over sine 8. And with your calculator, that gives you a negative 0.661. And since we already are given the position of the object at t equals 2, which is 1, 4, we can go ahead and write our equation. Y minus 4 equals negative 0.661 times x minus 1. All right, so for part C, it says to find the speed of the vector at t equals 2. So earlier we defined speed to be the square root of the derivative of the x term squared plus the derivative of the y term squared. Well, we have the derivative of the x term and we have the derivative of the y term. And we want it specifically at t equals 2. So I plug in t equals 2 to get the square root of sine 8 squared plus cosine 4 squared. And using my calculator to evaluate, I got 1.186. And for part D, find the position of the particle at t equals 1. Since we want to find the position of the particle at t equals 1, which is going backwards since we have the position at t equals 2. So we already have the position of the particle at t equals 2. Now we also need the distance it travels within that 1 to 2 time interval. And since we're working backwards, or the particle's moving backwards, we're going to have to subtract that distance. So that means that to find our position at t equals 1, we're going to take the position at t equals 2 and subtract the distance it travels from 1 to 2. And you're going to do the same thing with the y component. And the reason why you know you have to do both the x and the y components is because it does not specify which component. Sometimes the question will say specifically, find the horizontal position of the particle at t equals 1. In that case, you would only worry about the x component. But here it doesn't specify, so we have to do both. All right, so go ahead and set up each of the integrals. And I use my calculator to integrate and do the same thing with the y component. So that means that the position of the particle at t equals 1 is at 0.782, 4.443. All right, now this example has no calculator allowed. So the position of a particle at any time t greater than or equal to 0 is given by the x function of t squared minus 2 and the y function of 2/3 t cubed. We want to find the magnitude of the velocity vector at t equals 2. Now magnitude is basically the same thing as speed. So that means I need the derivative of both the horizontal and vertical component. So the derivative of the horizontal component is 2t, derivative of the y component is 2t squared. So therefore I can set up my square root of 2t squared plus 2t squared squared, which reduces to the square root of 4t squared plus 4t to the 4th. Since I'm looking specifically at t equals 2, I can go ahead and plug in 2 and simplify it down to 4 square root 5. For part B, it says set up an integral expression to find the total distance traveled by the particle from t equals 0 to t equals 4. Now, since it says set up, I'm not actually going to integrate anything. And since I want the total distance traveled between 0 and 4, here I have already found my magnitude of the velocity vector at any time t. So this is what I'm integrating. So basically, my distance is going to be from the integral from 0 to 4 of the square root of 4t squared plus 4t to the 4th dt. All right, part C says find dy dx as a function of x. So that means I need the derivative of my x component and my y component. And when I set up dy dx, that means I have the y derivative over the x derivative, which reduces just to t. But I want to rewrite this as a function of x. Well, we know that x of t is equal to t squared minus 2. So basically, I want to solve for t in my x component. So when I solve for t, I'm going to get t is equal to the square root of x plus 2. The reason why I'm not using the negative square root is because earlier in the problem, I defined t to always be positive. So therefore, my dy dx is given by the square root of x plus 2. All All right, part D says, at what time t is the particle on the y-axis? So this means at what time t is the x position 0. So that means we have 0 equals t squared minus 2. Solve for t. I'm only using the positive square root because t can't be negative. And that's it, because it's only asking me at what time t is the particle on the y-axis. It's at t equals square root 2. All right, let's look at the next example, which is also no calculator. An object moving along a curve in the xy plane has position x of t, y of t at time t with the velocity vector given by v of t, which is equal to 1 over t plus 1, comma 2t. At time t equals 1, the object is at the position natural log of 2, comma 4. So I want to find the position vector. So to find the position vector, I'm going to need to integrate each component of my velocity vector. So for my x component, I'm going to integrate 1 over t plus 1 dt. And for my y component, I'm going to integrate 2t dt. So when I integrate this one, I'm going to use u substitution, which will give me the natural log of t plus 1 plus c sub 1. The reason why I use c sub 1 is because I'm going to have another constant in the integral or the antiderivative of my y component, which is t squared plus c sub 2. Now I need to find the c's. Well, I know that when t equals 1, I have the following position. So for the x component, when t equals 1, x equals the natural log of 2. So then I can go ahead and set up my position function to solve for c. And when I do that, I get c equals 1. Or sorry, c equals 0. And then for the y component, when t equals 1, the y value equals 4. So I can set up that equation, solve for c equals 3. So therefore, my position vector is given by the natural log of t plus 1, comma t squared plus 3. All right, for part B, we are going to write an equation for the line tangent to the curve when t equals 1. So I need dy dx when t equals 1. So I put the derivative of the y component over the derivative of the x component, specifically at 1, to get 2 over 1/2, which just reduces down to 4. And I've already given the position of the curve at t equals 1, which is natural log of 2, comma 4. So when I write my equation, I have y minus 4 equals 4 times x minus the natural log of 2. All right, so for part C, it says to find the magnitude of the velocity vector when t equals 1. So magnitude is defined as the square root of the derivative of the x component squared plus the derivative of the y component squared. I already have those derivatives. And I can go ahead and plug in t equals 1. And when I simplify, I get the square root of 17 over 4, which is the square root of 17 over 2. All right, so part D says, at what time t greater than 0 does the line tangent to the particle x of t, y of t have a slope of 12? So basically what that means is at what time t is my dy dx equal to 12? Well, I first need my dy dx in terms of t. Well, we know dy dx is defined as the derivative of the y component over the derivative of the x component. After I do some simplifying, I get 2t times t plus 1. And I'm going to set that equal to 12. I distributed the t through, and I divided by 2 and got one side equal to 0, so that I now have a quadratic that I can factor to give me t plus 3 and t minus 2. So the only t value that works would be t equals 2 because t has to be greater than 0. Well, I hope you enjoyed learning the calculus behind vector functions, and I will see you in class tomorrow. Have a good night.